We will now do one more example of finding a Fourier series for a periodic function with period 2. So we're going to consider the periodic function f of x, where f of x equals x between -1 and 1. And we're going to extend f of x to be periodic so it has period 2. You can see the graph of that function f of x on the right. So we will note that L, which is half of my period, is 1. So to find the first Fourier coefficient A0, we want to do the inner product of f with 1 divided by the inner product of 1 with itself. In this case, the inner product of 1 with itself is, of course, 2. And we want to integrate from -1 to 1 f of x dx. Because that is the inner product of f of x with 1. So when I substitute in what f of x is between -1 and 1, I'm going to substitute in x. And I'm going to notice that x is an odd function. And because x is an odd function and I'm integrating over a symmetric interval from -1 to 1, I immediately see that that integral is 0. Now the rest of the a coefficients, a sub n, can be obtained by taking the inner product of f with cosine of nx n pi x. It's supposed to be cosine of n pi x over L, but in this case L is 1. And then I'm going to divide that by the inner product of cosine of n pi x with cosine of n pi x. So the denominator, the integral of cosine n pi x with itself, is going to be 1. So I get 1 over 1 times the numerator, which is the inner product of f with cosine n pi x. So that's the integral from -1 to 1 of f of x times cosine of n pi x dx. And in fact, this is equal to the integral from -1 to 1. Now f of x is going to be x on that interval from -1 to 1. And then we're going to have cosine of n pi x dx. And we're going to notice that x is an odd function and cosine of n pi x is an even function. And so when we multiply the odd function times an even function, we get an odd function. And if we integrate that odd function over a symmetric interval from -1 to 1, we in fact get 0. So that means that all of the coefficients a sub n, these are the coefficients of cosine of n pi x, all of those end up being 0. So what is b sub n? B sub n is going to be the inner product of f with sine of n pi x divided by the inner product of sine of n pi x with itself. The denominator is going to be the integral of sine of n pi x times itself from -1 to 1. We already know that that's going to be 1, or L in this case. And then the numerator is the integral from -1 to 1 of f of x times sine of n pi x dx. Well, let's look at that. This is going to be the integral from -1 to 1 of f of x, which on that interval is x times sine of n pi x dx. And I'm going to notice that x is an odd function and that sine is an odd function. So their product is even. So I'm going to rewrite this as 2 times the integral from 0 to 1 of x times sine of n pi x dx. Now in order to do that integral, I'm going to need to integrate by parts. So I'm going to let u be x and du be dx. And dv is going to be sine of n pi x dx. And so v is going to be a -1 over n pi cosine of n pi x. So if I'm integrating by parts, I'm going to leave my 2 on the outside here. And I'm going to get u times v, so minus x over n pi cosine of n pi x, evaluated between 0 and 1. And then minus a negative, so minus a negative 1 over 2 n pi. So in that case, I'm going to make it positive. Integral from 0 to 1 of 1 over n pi cosine n pi x dx. Okay, so we're going to get 2 times -1 over n pi cosine of n pi. And then minus a negative, when I plug in 0 for x, I just get 0. Because when I plug in 0 there for x, I will get 0. So that term goes away. And then I'm going to get a plus 1 over n squared pi squared sine of n pi x evaluated between 0 and 1. So I'm going to notice that the first term becomes 2 times -1 times -1 to the n. So notice here that this is going to be -1 to the n. So that gives me a -1 to the n plus 1 over n pi. And then sine of n pi is 0, and sine of 0 is 0. So everything here becomes 0. So my coefficients are just going to be 2 times -1 to the n plus 1 over n pi. So what is my function f of x? Okay, represented as a Fourier series. Well, the a0 term is 0. And then, so these are the a0s. And then the a sub n terms are also 0. So these are the sum of a sub n cosine of n pi x. Those turned out to be 0 as well. And then finally, I'm going to write the sum from n equals 1 to infinity of my b sub n's, which are 2 times -1 to the n plus 1 over n pi sine of n pi x. And we're saying then that the function x between -1 and 1, which has been extended to be periodic, can be represented by this Fourier series. We should notice that the function x is odd, and the only terms that we see in this series are odd terms, functions that are sine of n pi x. The constant term, which would be even, is not present, and none of the cosine n pi x's, which are even, are present. So an odd function in this case is going to be represented by a series entirely of odd functions. I just want to show you what it looks like in Desmos. So here I have plotted the series, in this case with 30 terms. I've also plotted the function x between -1 and 1. And you can see that the series looks like the function x repeated from -1 to 1 and then repeated with a period 2. And the only places where there's something funny going on is at the discontinuities, where you can see at the discontinuities that our function doesn't really look like that line segment that we're looking for. It starts to kind of unravel, and that allows it to jump down to the next period, and then of course it starts to get tighter again as it oscillates around that line segment of f of x equals x. Okay? The more terms that I use, the better the representation as of that line segment. But of course, you still have this weird behavior near the discontinuities where it doesn't quite wrap around the function f of x equals x as tightly.